Hello again, and welcome back to this quiet corner where big questions unfold slowly, where science meets wonder, and where the vastness of time becomes something we can hold gently in our minds. Wherever you find yourself tonight, whether tucked into bed with the covers pulled close, settled into a favorite chair as the day winds down, or walking under a sky full of distant stars, I'm glad you're here. If your thoughts are heavy, or your mind is racing, if the weight of the day still clings to your shoulders, let this be a place to rest. Tonight we're going to take a journey not through space, but through time, deep time, the kind that makes our worries feel small and our existence feel both fleeting and precious. We're going to explore one of the most inevitable and profound events in our cosmic future, the final days before the sun swallows the Earth. It's not a story of destruction, though destruction is part of it. It's a story of transformation, of cycles that have played out billions of times across the universe, of endings that are also beginnings. It's about the very star that warms your face on a spring morning, that powers the plants in your garden, that has made every sunset and sunrise possible since the first human looked up at the sky. That same gentle, reliable sun will someday grow into something unrecognizable, something magnificent and terrible, something that will fundamentally change what it means to exist in our corner of space. But this change won't happen tomorrow, or next year, or even in the next billion years. The timeline we're exploring stretches so far into the future that the entire history of human civilization, from the first cave paintings to the most advanced technology we can imagine, represents just the blink of an eye. In the time between now and then, our species might evolve beyond recognition, spread across the galaxy, or transform into something we can't even conceive. The Earth itself will see continents drift, new mountain ranges rise, countless ice ages come and go, and perhaps billions of new species emerge and flourish. Yet, despite this almost incomprehensible span of time, the story has a certain inevitability to it. Stars are not eternal. They are born, they live, and they die, following patterns that we've observed across the cosmos. Our sun, middle-aged and stable as it seems now, is no exception. It's currently about 4-6 billion years old, roughly halfway through its main sequence lifetime. For all those billions of years, it has been steadily converting hydrogen into helium in its core, releasing the energy that lights our days and drives our weather. But that process cannot continue forever. The fuel will run out, the balance that keeps our star stable will shift, and when it does, everything we know will change. This isn't a story of sudden catastrophe. The sun won't explode like a supernova, sending shockwaves across space. Instead, it will grow, slowly at first, over hundreds of millions of years. Then more rapidly, its outer layers will expand, becoming cooler but much larger, until our once familiar star becomes a red giant, hundreds of times its current size. By the end of this process, the sun's surface may extend beyond Earth's current orbit. The planet that has been our home, that has nurtured every life form we've ever known, will find itself inside the sun itself. But before we get to those final moments, there's so much more to explore. What will Earth look like in the billions of years before the sun begins its dramatic transformation? How will life adapt to the slowly changing conditions? What will happen to our oceans, our atmosphere, our climate as our star gradually brightens? And in those final epochs, as the sun begins its expansion, what will the experience be like for any beings still living on our world? Will they watch the sun grow larger in the sky, day by day, year by year? Will they migrate to the outer solar system, seeking refuge on moons that were once frozen wastelands but have become temperate worlds? Will they find ways to extend Earth's life, or will they simply witness its transformation with the kind of acceptance that comes from understanding cosmic cycles? These questions don't have neat answers, partly because we're dealing with timescales that dwarf human experience, and partly because so much can change between now and then. But we can piece together a story using what we know about stellar evolution, planetary dynamics, and the behavior of matter under extreme conditions. We can imagine what it might be like to live through these changes, to be part of a civilization so long-lived that it witnesses its home star's entire life cycle. And we can find in this distant future story something meaningful for our present moment. There's something deeply comforting about contemplating deep time, even when the story involves endings. It puts our daily struggles in perspective, reminds us that we're part of something much larger and longer lasting than our individual lives. It also highlights the preciousness of our current moment, this brief period when Earth is perfectly positioned, when the sun is stable and gentle, when life flourishes in countless forms. We're living during a golden age, cosmically speaking, and that realization can fill even our darkest nights with a kind of quiet wonder. As we move through this story together, we'll travel forward through time, watching the slow changes that will reshape our solar system. We'll see the sun gradually brighten, forcing life to adapt in ways we can barely imagine. We'll witness the beginning of the end of our star's stable phase, watch it start to run out of hydrogen fuel in its core. We'll experience the dramatic changes that follow, the sun's outer layers swelling, temperatures rising, the familiar blue sky of Earth giving way to something alien and extraordinary. We'll explore what happens to the other planets during this transformation, how the outer worlds that are frozen today might briefly become havens for life. We'll consider the possibility that by then intelligence and consciousness might have found ways to preserve themselves, to witness these cosmic events from safe distances, to carry the memory of Earth and humanity forward into whatever comes next. And finally, we'll contemplate those last days, hours, and moments before Earth is consumed by the sun. It has orbited faithfully for so long. What will it be like when our planet's surface begins to melt, when the oceans boil away, when the very rocks that have stood for billions of years finally surrender to the heat of their expanding star? It sounds terrifying, but there's also something oddly peaceful about it. A return to the stellar material from which Earth originally formed, a completion of a cycle that began in the death of earlier stars. This is not a story about fear or despair. It's a meditation on cycles, on the deep patterns that govern the universe, on the way endings and beginnings interweave throughout cosmic history. It's about the incredible journey that matter takes, from the hearts of ancient stars to the formation of planets, the emergence of life, the development of consciousness, and eventually back to stellar material again. We are all made of star stuff, as Carl Sagan famously said, and someday we will return to being star stuff, scattered by stellar winds to perhaps seed new worlds in distant parts of the galaxy. So settle in, let your breathing slow, and let your mind expand to embrace these vast timescales. We're about to take a journey through the longest story ever told, one that connects our present moment to the ultimate fate of our solar system. It's a story that's both ending and beginning, both deeply scientific and profoundly meaningful. As we explore the final days before the sun swallows the Earth, we'll discover that even endings can be beautiful when seen from the right perspective. The journey begins now, in the deep future, when the sun is no longer the star we know today, but something far more magnificent and dangerous. But to understand how we get there, we first need to understand what our sun is doing right now, in this moment, as you listen to these words under its ancient light. To understand the future of our sun, we must first appreciate what an extraordinary object it is right now. Every second, our star converts about 600 million tons of hydrogen into helium through nuclear fusion, releasing energy equivalent to billions of hydrogen bombs. This happens not through violent explosion, but through a controlled process that has been remarkably stable for billions of years. The sun maintains this stability through a delicate balance between the inward pull of gravity, which wants to collapse the star, and the outward pressure of radiation, which pushes against that collapse. This balance is not static. It's a dynamic equilibrium, constantly adjusting as conditions in the sun's core slowly change. The hydrogen fuel doesn't burn evenly throughout the sun's interior. Most of the fusion happens in the very center, where temperatures reach about 15 million degrees Celsius and pressures are enormous. Here, in a region smaller than a quarter of the sun's radius, virtually all of the star's energy is produced. As hydrogen converts to helium, the core gradually becomes richer in the heavier element. Helium nuclei are more massive than hydrogen nuclei, so the core becomes denser over time. This increased density causes the core to heat up slightly, which increases the rate of fusion reactions. The result is that the sun is actually getting brighter very slowly, increasing its luminosity by about 10% every billion years. This gradual brightening might seem insignificant, but it has profound implications for Earth. A billion years ago, the sun was about 90% as bright as it is today. 4 billion years from now, it will be about 40% brighter than it is now. This change alone will dramatically alter conditions on our planet. Long before the sun begins its red giant phase, the sun's structure is more complex than it might appear from our distant perspective. The energy-producing core is surrounded by the radiative zone, where energy moves outward primarily through radiation. Photons created in the core bounce around in this region for hundreds of thousands of years before finally reaching the outer layers. Above the radiative zone is the convective zone, where hot material rises and cooler material sinks, creating the rolling motions that transport energy to the surface. The visible surface of the sun, called the photosphere, is where the light we see originates. Above this lies the chromosphere, and then the corona, the sun's outer atmosphere, which extends millions of kilometers into space. The corona is much hotter than the photosphere, a puzzle that scientists are still working to understand fully. Solar wind, a stream of charged particles, flows outward from the corona, carrying the sun's influence throughout the solar system. Currently, the sun is classified as a yellow dwarf star, though it's actually more white than yellow when seen from space. Earth's atmosphere gives it its golden appearance. As stars go, the sun is remarkably ordinary, neither particularly large nor small, neither especially hot nor cool. This ordinariness is actually extraordinary for us, because it means the sun is stable and long-lived, providing the steady energy source that complex life requires. Stars much more massive than the sun burn through their fuel, much faster, and live shorter lives. They might last only millions of years before exploding as supernovae. Stars much less massive burn their fuel so slowly that they can shine for trillions of years, but they're also much dimmer, which means planets have to orbit very close to stay warm enough for liquid water. These close-in planets are likely to be tidally locked, with one side always facing the star and the other always dark. Our sun hits a sweet spot, massive enough to be bright and stable, but not so massive that it burns out quickly. The sun's magnetic field is another crucial aspect of its current behavior. This field is generated by the movement of charged particles in the sun's interior, creating a complex, ever-changing magnetic environment. The sun's magnetic field reverses polarity about every 11 years, creating what we call the solar cycle. During periods of high magnetic activity, we see more sunspots, solar flares, and coronal mass ejections. During quieter periods, the sun appears relatively smooth and calm. These magnetic phenomena affect Earth in subtle but important ways. Solar flares can disrupt radio communications and satellite operations. Coronal mass ejections can cause geomagnetic storms that produce beautiful auroras, but can also damage power grids and electronic systems. Throughout Earth's history, variations in solar activity have influenced our planet's climate in ways we're still studying. As we look toward the distant future, it's important to understand that the sun's magnetic field will continue to play a role in how it evolves. During the red giant phase, the sun's magnetic field will become even more complex and dynamic, potentially affecting how it loses mass and how its outer layers behave. The solar wind will strengthen dramatically, carrying away substantial portions of the Sun's mass and potentially affecting any remaining planets. The Sun's current mass is about 30,000 times that of Earth, containing 99.86% of all the mass in our solar system. This enormous gravitational influence holds the planets in their orbits and has shaped the architecture of our solar system since its formation 4.6 billion years ago. But during its evolution into a red giant, the Sun will lose a significant fraction of its mass through stellar winds. This mass loss will cause the planet's orbits to expand, potentially saving some worlds from being consumed by the expanding star. Understanding the Sun as it is now helps us appreciate what a remarkable phase of stellar evolution we're currently experiencing. The Sun is in its prime, steadily converting hydrogen to helium, providing stable energy output, maintaining a relatively calm magnetic environment. This is the phase that has allowed life to develop and flourish on Earth. It's the phase during which intelligence emerged, looked up at the sky, and began to wonder about its place in the cosmos. But this phase won't last forever. The hydrogen fuel in the Sun's core is finite, and we can calculate with reasonable precision when it will run out. In about 5 billion years, the Sun will have converted enough hydrogen to helium that the core will no longer be able to sustain the fusion reactions that power the star. When that happens, the Sun will begin the next phase of its evolution, and everything in our solar system will begin to change. Before we explore that dramatic transition though, let's consider what will happen to Earth during the long, slow brightening phase that's already underway. How will our planet change as the Sun gradually becomes more luminous? How will life adapt to these slowly shifting conditions? And what will Earth look like during those final billion years before the Sun begins its transformation into a red giant? The story of Earth's future is intimately connected to the story of the Sun's evolution, but it's also influenced by countless other factors: plate tectonics, atmospheric evolution, the carbon cycle, the behavior of life itself. Over the next billion years, all of these elements will interact in complex ways, creating a world that may be barely recognizable compared to the Earth we know today. As the Sun gradually brightens over the next billion years, Earth will experience changes so slow they would be imperceptible from one generation to the next, yet so profound that they will eventually transform our planet beyond recognition. The additional solar energy reaching Earth will trigger a series of feedback loops that will fundamentally alter our climate system, our oceans, and the very composition of our atmosphere. The first and most direct effect of increased solar luminosity will be rising temperatures. Even a 10% increase in the Sun's brightness, which will occur over the next billion years, will add significant energy to Earth's climate system. This might not sound like much, but consider that the difference between our current climate and the last ice age was only about a 6-degree change in global average temperature, caused by much smaller variations in solar heating due to orbital cycles. As temperatures rise, more water will evaporate from the oceans. Water vapor is itself a greenhouse gas, so this will amplify the warming effect. The increased humidity will also change cloud formation patterns. Some types of clouds cool the planet by reflecting sunlight back to space, while others trap heat like a blanket. The net effect of changing cloud patterns is one of the most complex aspects of climate science, even for current conditions, and becomes even more challenging to predict over billion-year timescales. The warming oceans will affect currents and weather patterns in ways we can only begin to imagine. The great conveyor belt of ocean circulation that currently helps regulate Earth's climate by distributing heat around the globe will shift and potentially reorganize entirely. Regions that are currently temperate might become tropical, while polar regions experience conditions more like today's mid-latitudes. Ice will be among the first casualties of the brightening Sun. The polar ice caps, which currently reflect much of the sunlight that hits them, will shrink and eventually disappear entirely. This will create another positive feedback loop, as dark ocean water absorbs much more heat than reflective ice. Sea levels will rise as ice sheets melt, potentially by hundreds of meters over such long timescales. Coastal areas that are currently dry land will become shallow seas, but the most profound changes may occur in the atmosphere itself. As temperatures continue to rise, Earth's atmosphere will begin to lose water to space through a process called hydrodynamic escape. The upper atmosphere will heat up, causing water molecules to move faster and eventually reach escape velocity. This process is irreversible. Once water molecules escape to space, they don't return. Venus provides a cautionary example of how this process can unfold. Early in its history, Venus likely had oceans similar to Earth's, but as the sun gradually brightened over billions of years, Venus experienced a runaway greenhouse effect. Its oceans boiled away, the water vapor was lost to space, and what remained was the hellish world we see today, with surface temperatures hot enough to melt lead and atmospheric pressures nearly 100 times greater than Earth's. Earth has several advantages that Venus lacked. We're farther from the sun, so we'll experience the effects of solar brightening more gradually. We also have a strong magnetic field that helps protect our atmosphere from being stripped away by the solar wind. Most importantly, we have plate tectonics, which plays a crucial role in regulating our planet's climate through the carbon cycle. The carbon cycle is one of Earth's most important long-term climate regulation systems. Carbon dioxide dissolves in rainwater, forming weak carbonic acid that weathers rocks and minerals. The resulting dissolved minerals and carbon compounds wash into the oceans, where they eventually precipitate as limestone and other carbonate rocks. This process removes carbon dioxide from the atmosphere. Meanwhile, volcanic activity and the slow recycling of crustal material through plate tectonics gradually returns carbon dioxide to the atmosphere. As the sun brightens and Earth warms, this carbon cycle will accelerate. Higher temperatures will increase the rate of rock weathering, pulling more carbon dioxide out of the atmosphere. In the short term, this acts as a natural thermostat, helping to keep Earth's climate stable even as solar luminosity increases. This negative feedback mechanism explains how Earth has maintained liquid water on its surface for billions of years, despite the gradual brightening of the sun. But this thermostat has limits. As carbon dioxide levels in the atmosphere drop due to increased weathering, plants will face a crisis. Most plants require a minimum level of atmospheric carbon dioxide for photosynthesis. When CO2 levels drop below about 150 parts per million, most plant species cannot survive. Currently, atmospheric CO2 is around 420 parts per million, elevated due to human activity, but even the pre-industrial level of about 280 parts per million is well above the critical threshold. However, as the carbon cycle continues to accelerate in response to rising temperatures, atmospheric CO2 will continue to decline. In perhaps 500 million to 1 billion years, CO2 levels will drop below the threshold needed for most plant life. When this happens, the foundation of Earth's food web will collapse. Without plants to produce oxygen through photosynthesis, atmospheric oxygen levels will also begin to decline. The loss of plant life will represent one of the most dramatic transitions in Earth's history. For over 3 billion years, photosynthetic organisms have been the primary producers in Earth's ecosystems, converting sunlight and carbon dioxide into organic compounds that feed virtually all other life forms. The end of the photosynthetic era will mark the beginning of the end for complex life as we know it. Some organisms might adapt to these changing conditions. Deep-sea ecosystems around hydrothermal vents, which rely on chemosynthesis rather than photosynthesis, might persist longer than surface-dwelling life. Microorganisms are incredibly adaptable and have survived every mass extinction event in Earth's history. Some bacteria and archaea might find ways to survive even as conditions become increasingly hostile. But for large, complex organisms, the future looks bleak. As plant life disappears, herbivores will have no food source. As herbivores die out, carnivores will follow. The intricate ecosystems that currently cover Earth's surface will collapse one by one. starting with the most sensitive environments and spreading to more resilient habitats. The oceans will face their own crisis as temperatures continue to rise. Hot water holds less dissolved oxygen than cold water, and as the oceans heat up, vast dead zones will expand. Marine life will be forced into increasingly small refugia in polar regions or at great depths where temperatures remain tolerable. As we move deeper into this warming phase, Earth's climate will become increasingly unstable. The gradual, predictable changes of the early stages will give way to more chaotic and unpredictable shifts. Weather patterns that have persisted for millions of years may break down entirely. Storms of unprecedented intensity may sweep across continents that have become deserts. The geological processes that have shaped Earth for billions of years will also be affected. Extreme heat will alter the behavior of rocks and minerals at the surface. New types of geological formations may emerge under conditions that have never existed before in Earth's history. The very landscape will begin to transform in preparation for the even more dramatic changes to come. During this period, any remaining life will be concentrated in the most favorable locations, perhaps deep underground, where temperatures remain moderate and water might still exist, perhaps in caves or other sheltered environments, perhaps at the very poles, which will be the last places to experience tolerable temperatures. This is the world that will greet the sun's transition into its red giant phase, not the blue marble we know today, with its white clouds and green continents, but a baked, largely lifeless world with a thin atmosphere and empty oceans. It will be a planet that has already been through its own apocalypse, transformed by the relentless increase in solar energy into something almost unrecognizable. Yet even this devastated world will face an even greater challenge when the sun finally exhausts the hydrogen fuel in its core and begins to expand. The gentle warming of the past billion years will seem mild compared to what comes next. As we'll explore in the coming sections, the sun's transformation into a red giant will bring changes so dramatic that they will make the previous billion years of warming seem like a minor fluctuation. But before we witness those final catastrophic days, let's take a moment to understand exactly what happens inside a star when it begins to die, and why this process leads to the spectacular expansion that will eventually engulf our planet. The transformation of our sun from a stable, hydrogen-burning star into a red giant is one of the most well-understood processes in astronomy, yet it remains one of the most dramatic events that can occur in a solar system. This change doesn't happen suddenly, but unfolds over hundreds of millions of years, following physical laws that govern the behavior of matter under extreme conditions. The process begins in the sun's core, where nuclear fusion has been steadily converting hydrogen into helium for over 4 billion years. This fusion reaction occurs when hydrogen nuclei, essentially single protons, combine to form helium nuclei, which consist of 2 protons and 2 neutrons. The mass of a helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei required to create it. This small difference in mass is converted to energy, according to Einstein's famous equation, E=mc², releasing the tremendous amounts of energy that power the sun. As billions of years pass, the core gradually becomes enriched in helium while becoming depleted in hydrogen. Helium nuclei are heavier than hydrogen nuclei, so the core becomes denser as the composition changes. This increased density causes the core to contract slightly under its own gravity, which raises its temperature. The higher temperature increases the rate of hydrogen fusion in the remaining fuel, causing the sun to become gradually brighter over time. This process continues until the hydrogen in the core is essentially exhausted. At this point, about 5 billion years in the future, the core will be composed almost entirely of helium, with no hydrogen left to fuse. Without nuclear fusion to provide outward pressure, the core will begin to contract under the immense weight of the outer layers pressing down on it. As the helium core contracts, it heats up dramatically, but helium fusion requires much higher temperatures than hydrogen fusion. The core must reach about 100 million degrees Celsius before helium nuclei can overcome their electrical repulsion and fuse together. Until the core reaches this temperature, no fusion reactions can occur there, and the core will continue to contract and heat up. Meanwhile, the contraction and heating of the core will create a shell of hot, dense material around it. This shell will be rich in hydrogen and will reach temperatures hot enough to sustain hydrogen fusion. Suddenly, the sun will have a new energy source, hydrogen burning in a shell around the inert helium core. This shell burning will actually produce more energy than the sun's current core fusion process. The dramatic increase in energy production will have profound effects on the sun's outer layers. The additional energy will cause these outer layers to expand enormously, creating what astronomers call a red giant star. The sun's surface will move outward, perhaps reaching as far as Earth's current orbit, while the surface temperature drops to about 3000 degrees Celsius, giving the expanded star a distinctly red color. This expansion will occur relatively rapidly by stellar standards, taking perhaps 100 million years to complete. During this time, the sun's luminosity will increase dramatically, potentially becoming thousands of times brighter than it is today. However, because this increased energy is spread over a much larger surface area, each square meter of the sun's surface will actually be cooler and dimmer than it is now. The red giant phase is inherently unstable compared to the sun's current main sequence phase. The outer layers of a red giant are only weakly bound to the star, and strong stellar winds will carry away significant amounts of material. The sun may lose 25% or more of its mass during this phase, creating beautiful but ephemeral planetary nebulae as the expelled material forms glowing shells around the dying star. Eventually, the contracting helium core will reach the critical temperature of 100 million degrees, and helium fusion will begin. This event, called the helium flash, will occur quite suddenly and will produce an enormous burst of energy. For a brief period, the core will produce more energy through helium fusion than the sun currently produces through hydrogen fusion. This will cause the star to restructure itself, potentially becoming somewhat smaller and hotter than during the early red giant phase. The helium burning phase will be much shorter than the hydrogen burning phase that has sustained the sun for billions of years. Helium fusion produces carbon and oxygen, and the energy release per gram of fuel is lower than for hydrogen fusion. The sun will have perhaps 100 million years of helium burning before this fuel too is exhausted. Once the helium in the core is consumed, the sun will face another crisis. Carbon and oxygen fusion require even higher temperatures than helium fusion, temperatures that the sun's core will never reach. The sun is simply not massive enough to compress its core to the extreme densities and temperatures needed for these reactions. More massive stars can continue fusing heavier elements all the way up to iron, but for solar mass stars, the fusion process effectively ends with helium. Without nuclear fusion to support it, the core, now composed of carbon and oxygen, will contract into an extremely dense object called a white dwarf. Meanwhile, the outer layers will continue to expand and will eventually be expelled entirely, creating a planetary nebula. The sun will essentially blow off its outer atmosphere, leaving behind only the hot, dense core. This entire process, from the exhaustion of core hydrogen to the formation of a planetary nebula, will take perhaps 1 to 2 billion years. During the most dramatic phases, when the sun is at its largest as a red giant, it may extend beyond the orbit of Earth. Whether our planet is actually engulfed will depend on several factors, including exactly how large the sun becomes and how much mass it loses during the expansion process. The mass loss is particularly important because it affects planetary orbits. As the sun loses mass, its gravitational pull weakens and planetary orbits expand. If the sun loses enough mass quickly enough, Earth's orbit might expand fast enough to keep it outside the sun's photosphere, even during the red giant's maximum size. However, even if Earth avoids being directly consumed, it will be subjected to intense heat and radiation that will make it completely uninhabitable. The physics of this stellar evolution process is well understood, because we can observe similar stars throughout the galaxy in various stages of this same transformation. We can see stars that are just beginning to exhaust their core hydrogen, others that are in full red giant phase, and still others that have already expelled their outer layers to become white dwarfs surrounded by glowing planetary nebula. What makes this story both fascinating and sobering is its inevitability. Unlike many other cosmic threats, which might or might not occur, stellar evolution follows predictable patterns based on well-established physics. We can calculate with confidence when the sun will begin its red giant phase, how long it will last, and what the general characteristics will be. The details may vary, and there's uncertainty about exactly how events will unfold, but the broad outline is as certain as any prediction can be over such vast timescales. For any beings living in the solar system during this transition, the changes will be both gradual and dramatic. The gradual brightening over hundreds of millions of years will be followed by more rapid expansion and dramatic increases in heat and radiation. The familiar sun that has been a constant presence throughout Earth's history will transform into an alien, enormous star that dominates the sky. This transformation will not only affect Earth, but will reshape the entire solar system. Planets, moons, asteroids, and comets will all experience conditions unlike anything in their previous history. Some worlds that are currently frozen wastelands might briefly become habitable, while others will be scorched beyond recognition. The careful gravitational balance that has kept the solar system stable for billions of years will shift as the sun loses mass and changes its energy output. As we prepare to explore what these changes mean for Earth specifically, it's worth pausing to appreciate the remarkable nature of this cosmic story. The same nuclear processes that currently warm our days and drive our weather will eventually transform our sun into something magnificent and terrible. The star that has made life possible will become the agent of its destruction. Yet this is not a story of malice or accident, but of natural processes following their inevitable course, part of the grand cycle of stellar birth, evolution, and death that has shaped the universe since its beginning. The final chapter of Earth's story begins not with a bang, but with a sunrise that will never end. As the sun enters its red giant phase, our planet will experience its last dawn as a potentially habitable world, but this dawn will be unlike any in Earth's 4.5 billion year history, as the expanding sun begins to fill more and more of the sky, bringing with it conditions that will systematically dismantle every system that has supported life. The transformation won't happen overnight. The sun's expansion from its current size to red giant dimensions will take place over roughly 100 million years, a timescale so long that mountains could rise and erode away several times over. Yet, by astronomical standards, this is rapid change, and the effects on Earth will be profound and accelerating. During the early stages of expansion, Earth will still be recognizable, though profoundly changed from the warming that occurred during the previous billion years. The planet will likely be a desert world by this point, with most surface water already lost to space and atmospheric CO2 levels too low to support plant life. But as the sun begins to expand, even these harsh conditions will seem mild compared to what's coming. The first noticeable change will be the sun's appearance in Earth's sky. Throughout human history, the sun has appeared as a disk roughly half a degree wide, about the same apparent size as the moon. This familiar sight will gradually change as the sun's physical diameter increases. Day by day, month by month, year by year, the sun will grow larger in the sky. At first, the change will be imperceptible, requiring careful measurements to detect, but as the expansion continues, it will become obvious even to casual observers. As the sun grows larger, it will also grow brighter, but not uniformly. The total energy output will increase dramatically, but the surface temperature will actually decrease, giving the sun a redder color than the yellow-white we know today. This means that Earth will receive much more infrared radiation and somewhat less visible light. The familiar blue sky of Earth already likely gone due to atmospheric changes during the preceding billion years of warming, will give way to something entirely alien. The increased energy input will drive Earth's surface temperature ever higher. Any remaining ice will vaporize instantly. Rocks will begin to glow red-hot, then yellow-hot, then white-hot as temperatures continue to climb. The solid surface that has been stable for billions of years will begin to soften and eventually melt. Earth's crust will become a global ocean of molten rock, with temperatures reaching thousands of degrees. The atmosphere, already thin and depleted, will begin to boil away entirely. What remains of Earth's air will expand and escape to space, no longer held by the planet's gravity against the intense heating. Any water vapor remaining from earlier epochs will break apart into hydrogen and oxygen. The hydrogen will escape to space, while the oxygen may temporarily enrich the escaping atmosphere before it too is lost. As Earth heats up, fascinating geological processes will unfold. Minerals that have been stable for billions of years will transform into new phases that can only exist at extreme temperatures. The very chemistry of rock will change. Granite, limestone, sandstone, and all the familiar rock types will melt and mix together in a global magma ocean. New types of volcanic activity, anything in Earth's previous history, may create towering eruptions that reach hundreds of kilometers into the thinning atmosphere. The planet's magnetic field, generated by the motion of liquid iron in Earth's core, will likely persist through these changes, though it may become unstable as temperature differences between the core and surface decrease. Without the protection of a substantial atmosphere, however, the magnetic field will provide little defense against the increasingly intense solar radiation. During this period, Earth's orbit itself may begin to change. The red giant sun will have a much more extended atmosphere than the current sun, and Earth will begin to experience atmospheric drag as it orbits through the outer layers of the expanded star. This will cause Earth's orbit to decay, spiraling slowly inward. Additionally, the sun will be losing mass through stellar winds, which will cause Earth's orbit to expand outward. These competing effects make it difficult to predict exactly where Earth will be when the sun reaches maximum size. Tidal forces will also come into play as Earth orbits within or near the sun's outer atmosphere. Just as the moon raises tides in Earth's oceans, the sun will exert tidal forces on the molten Earth. These forces may cause the planet to become elongated, stretched out in the direction of the sun. The familiar spherical shape that Earth has maintained throughout its history may give way to a more egg-like form. As the sun continues to expand and Earth continues to heat up, even more dramatic changes will occur. The molten rock surface will begin to vaporize, creating an atmosphere of rock vapor that will eventually be stripped away by the solar wind. Earth will literally evaporate, starting with the lighter elements and compounds, and gradually working its way through the entire periodic table. The process of evaporation won't be uniform across the planet. The side facing the sun will heat up more rapidly and lose material faster than the side facing away. This may cause Earth to develop a comet-like tail of vaporized rock and metal streaming away from the sun. From a distance, if any observers existed to witness it, Earth might resemble a giant comet rather than a planet. During the most intense phases of this process, Earth's surface temperature will rival that of the sun's surface. The distinction between planet and star will begin to blur as Earth glows white-hot, radiating energy back into space. The familiar concepts of day and night will become meaningless, as every part of the planet receives continuous intense heating. Eventually, the sun will reach its maximum size as a red giant. Depending on the exact details of stellar evolution, which vary from model to model, the sun's surface may extend beyond Earth's orbital distance. If this happens, Earth will find itself inside the sun, orbiting within the star's outer atmosphere. The conditions will be indescribable by any earthly standards, with temperatures, pressures, and radiation levels that dwarf anything our planet has ever experienced. Even if Earth's orbit expands enough to keep it outside the sun's photosphere, The planet will be bathed in radiation and stellar material that will continue the process of evaporation and erosion. The gravitational binding energy that has held Earth together for 4.5 billion years will finally be overcome by the thermal energy supplied by the Sun. The planet will literally come apart, its material mixing with the solar wind and spreading throughout the inner solar system. The fate of Earth's material won't be complete destruction. The atoms that make up our planet, forged in the hearts of ancient stars and assembled over billions of years of cosmic evolution, will be recycled once again. Some may condense into new planets around other stars. Some may drift through space for eons before finding new homes. The carbon that was once part of Earth's life forms, the oxygen that filled its atmosphere, the silicon that formed its rocks, all will continue their cosmic journey. This dissolution of Earth represents not just an ending, but a return to the cosmic processes that created the planet in the first place. Earth formed from the debris of earlier stellar explosions, and it will return to being stellar debris, available to seed new worlds in new solar systems. In this sense, the Sun swallowing Earth is less like destruction and more like a cosmic recycling program, breaking down old structures to create the raw materials for new ones. The timeline for these final processes is difficult to predict precisely, as it depends on many factors, including the exact size the Sun reaches, how much mass it loses, and how Earth's orbit evolves. The final evaporation of the planet might take anywhere from thousands to millions of years, once conditions become extreme enough. From the perspective of any hypothetical observers, it would be a gradual fading rather than a sudden disappearance. These final days represent the end of a story that began 4.6 billion years ago, when dust and gas in a stellar nursery first began to collapse under gravity, forming the Sun and its planets. Earth's biography will span nearly the entire main sequence lifetime of its parent star, making it a remarkably successful experiment in planetary evolution. Few planets in the universe will have such a long, stable history. As we contemplate these ultimate events, it's worth remembering that this story plays out not just for Earth, but for countless other worlds throughout the galaxy. Every sun-like star will eventually become a red giant, and every terrestrial planet in the inner regions of these systems will face a similar fate. This is not a cosmic tragedy, but simply the way the universe works, the natural endpoint of stellar and planetary evolution. The Sun swallowing Earth is, in many ways, a return home. We are made of star stuff, and we will return to being star stuff, scattered by stellar winds to perhaps someday become part of new worlds orbiting younger stars. This is the deep story of the cosmos, the endless cycle of birth, evolution, death, and renewal that has been playing out for billions of years and will continue for billions more. While Earth faces its ultimate fate in the expanding Sun, the outer regions of our solar system will experience what might be called a cosmic renaissance. Worlds that have been frozen wastelands for their entire existence will briefly bask in warmth and energy, potentially becoming oases of habitability in the dying solar system. This transformation of the outer solar system represents one of the most intriguing aspects of stellar evolution and raises fascinating questions about the nature of life and habitability. As the Sun expands into a red giant, its luminosity will increase dramatically, perhaps by a factor of several thousand. This enormous increase in energy output will push the habitable zone, the region where liquid water can exist on a planet's surface, far outward from its current location. Today, the habitable zone encompasses the region from about Venus's orbit to just beyond Mars. During the red giant phase, it may extend from the current orbit of Jupiter out to Saturn or even farther. This shift will transform worlds that have never known warmth into potentially habitable environments. Jupiter's moons Io, Europa, Ganymede, and Callisto will receive intense solar heating for the first time in their history. Europa and Ganymede, which currently harbor subsurface oceans beneath thick ice shells, may see those ice shells melt completely, revealing global oceans open to space. The transformation of Europa would be particularly dramatic. Currently, this moon is covered by a smooth ice shell, perhaps 15 to 25 kilometers thick, beneath which lies an ocean that may contain twice as much water as all of Earth's oceans combined. As the sun expands and brightens, Europa's ice shell will begin to melt from above, while tidal heating from Jupiter continues to warm it from below. The result could be a world with a deep global ocean and a relatively thin atmosphere created by sublimating ice. Ganymede, the largest moon in the solar system, would undergo an even more spectacular transformation. Currently differentiated into a rocky core, ice water mantle, and ice shell, Ganymede would see its surface ice melt to reveal an ocean deeper than Europa's. Unlike Europa, Ganymede has its own magnetic field, which would provide some protection for any life that might emerge in its newly accessible oceans. Callisto, the most heavily cratered object in the solar system, would also thaw during this period. Its ancient scarred surface, which has preserved a record of the early solar system's bombardment history, would disappear beneath a global ocean. The heavy cratering that tells the story of the solar system's violent youth would be hidden forever under liquid water. Even Io, currently the most volcanically active body in the solar system due to tidal heating from Jupiter, would experience changes. The increased solar heating would add to its already intense geological activity, potentially creating an even more dynamic and unstable surface. Io's thin atmosphere, currently composed mainly of sulfur dioxide from volcanic outgassing, might thicken and change composition as different materials begin to sublimate in the increased heat. Saturn's moons would undergo similar transformations. Titan, already one of the most intriguing worlds in the solar system with its thick atmosphere and lakes of liquid methane, would experience a complete climate revolution. Currently, Titan's surface temperature is about 79 degrees C, cold enough to keep water frozen, as hard as rock while allowing methane to exist as a liquid. As the sun's energy increases, Titan's surface would warm dramatically. The warming of Titan might proceed in stages. First, the methane lakes would evaporate, thickening the atmosphere and potentially creating a runaway greenhouse effect. Similar to what occurred on Venus, the thick atmosphere might trap enough heat to begin melting the water ice that makes up much of Titan's surface. If the warming continued far enough, Titan might develop a water ocean beneath a thick, methane-rich atmosphere. Enceladus, which currently harbors a subsurface ocean beneath its south polar region, would likely see that ocean break through to the surface. The spectacular ice geysers that currently spray from the moon's south pole would become much more active, potentially creating a thin atmosphere of water vapor around this small world. The transformation of these moons from frozen wastelands to potentially habitable worlds would occur relatively rapidly by geological standards, perhaps over a few million years. This is an incredibly short time for biological evolution, but it might be long enough for existing life forms to adapt to changing conditions, if such life forms exist in the subsurface oceans of these moons. The possibility that life already exists in these hidden oceans is one of the most exciting prospects in astrobiology. Europa, Enceladus, and possibly Ganymede and Callisto all show evidence of liquid water oceans beneath their ice shells. These oceans have existed for billions of years, potentially providing stable environments where life could have evolved. If such life exists, the opening of these oceans to space during the sun's red giant phase would represent a dramatic expansion of accessible habitat. However, the transition would also bring challenges for any existing life. The sudden exposure to space would subject these ecosystems to radiation, temperature fluctuations, and the loss of atmosphere that they've never experienced before. Life that evolved in the dark, high-pressure environment beneath kilometers of ice would suddenly find itself in direct sunlight with greatly reduced pressure. Some organisms might adapt to these new conditions. Life on Earth has shown remarkable resilience and adaptability, surviving in environments from deep ocean trenches to the upper atmosphere. If life exists in the outer solar system's hidden oceans, Some forms might evolve to take advantage of the new energy sources and surface habitats that become available. The increased solar energy would also drive new chemical processes on these worlds. Currently, the chemistry of the outer solar system is dominated by low-temperature reactions and the slow radiolysis of water and organic compounds by cosmic rays and Jupiter's radiation field. With abundant solar energy, photochemistry would become dominant for the first time, potentially creating new organic compounds and atmospheric compositions. The duration of this habitable period would depend on how long the Sun remains in its red giant phase. Current models suggest this phase could last anywhere from a few 100 million to over 1 billion years, depending on the Sun's exact mass and the details of its evolution. This is a substantial period, long enough for significant biological evolution to occur if life already exists, or for life to potentially emerge from scratch. Farther out in the solar system, even more distant worlds might experience brief periods of habitability. Uranus and Neptune, the ice giants, would receive enough energy to warm their upper atmospheres and potentially drive interesting atmospheric chemistry. Their moons, currently frozen solid, might briefly experience surface melting. The dwarf planets of the outer solar system, including Pluto, Eris, and others, would also warm significantly. Pluto's thin atmosphere of nitrogen, methane, and carbon monoxide would thicken as ices sublime. The planet might develop weather patterns and atmospheric dynamics for the first time in its history. The binary nature of the Pluto-Charon system might create unique tidal effects as both bodies warm and potentially develop atmospheres. The Kuiper Belt, the region of icy bodies beyond Neptune's orbit, would become a hive of activity as countless small worlds begin to outgas and develop temporary atmospheres. Comets that normally only become active when they venture into the inner solar system would suddenly find themselves in permanently warm conditions, creating spectacular tails and comas that might persist for millions of years. This transformation of the outer solar system would create a brief golden age for exploration and discovery, if any advanced civilizations still exist to take advantage of it. Worlds that were previously accessible only to the most sophisticated robotic probes might become destinations for easier exploration, their surfaces and oceans finally exposed to direct study. The irony is profound. Just as the inner solar system becomes uninhabitable due to the Sun's expansion, the outer solar system experiences its first and only period of widespread habitability. This cosmic reshuffling of the habitable zone represents one of the universe's grandest experiments in the redistribution of life-supporting conditions. Yet this renaissance would be temporary, as the Sun continues through its red giant phase, eventually exhausting its helium fuel and beginning to shed its outer layers. The energy output would become increasingly unstable. The steady warmth that briefly made the outer worlds habitable would give way to violent fluctuations in energy and massive ejections of stellar material that would sterilize these newly thawed worlds. The final phases of the Sun's evolution would see the formation of a planetary nebula as the outer layers are expelled, leaving behind a white dwarf star with only a tiny fraction of the Sun's current energy output. The brief summer experienced by the outer solar system would end in a winter far more severe than any they had previously known, as the fading white dwarf provides barely enough energy to keep even the closest remaining worlds above absolute zero. This cycle of freezing, thawing, and freezing again represents the ultimate fate of planetary systems around Sun-like stars throughout the galaxy. It's a reminder that habitability is not a permanent condition, but a temporary state that depends on the continuing evolution of stellar energy sources. The story of life, wherever it exists, is intimately connected to the life cycles of stars. As we contemplate this cosmic transformation, we're reminded that the universe operates on scales that dwarf human experience, yet follow patterns that we can understand and predict. The same physical laws that govern the behavior of gas in a laboratory also determine the fate of stars and planets across cosmic time. In this vast story of stellar evolution and planetary transformation, we find both the insignificance and the profound significance of our place in the cosmos. As the sun's red giant phase reaches its climax and the outer solar system enjoys its brief renaissance, an even more dramatic transformation awaits. The helium burning in the sun's core cannot continue indefinitely, and when this fuel is exhausted, the star will face its final crisis. The death throes of our sun will create some of the most beautiful and violent phenomena in astronomy, reshaping what remains of the solar system one last time. The end begins when the sun exhausts the helium in its core, leaving behind a dense ball of carbon and oxygen. Unlike more massive stars which can continue fusing heavier elements, the sun lacks the mass necessary to compress its core to the extreme temperatures required for carbon fusion. With no nuclear reactions to provide outward pressure, the core will contract under its own gravity, becoming extremely hot and dense. This contraction will drive the temperature in the surrounding helium-burning shell to ever higher levels, causing the shell to burn more and more violently. The energy production will become erratic and unstable, causing the sun to pulsate dramatically. During this phase, known as the asymptotic giant branch, the sun will alternately expand and contract, with periods of relative stability interrupted by violent outbursts. These thermal pulses will be among the most energetic events in the sun's entire lifetime. During each pulse, the energy production may increase by factors of hundreds or thousands, causing the outer layers of the star to expand rapidly. The sun's radius may fluctuate wildly, sometimes reaching dimensions larger than the orbit of Mars, then contracting again to a smaller size. The instability of this phase will have catastrophic effects on any remaining objects in the inner solar system. The varying energy output will subject planets and moons to extreme temperature swings. Any world that survived the initial red giant expansion will face conditions that change dramatically over periods of thousands to tens of thousands of years. No stable climate could exist under such conditions. The stellar winds during this phase will be far more intense than anything experienced during the earlier red giant evolution. The sun will lose mass at an accelerated rate, ejecting perhaps 50% or more of its remaining material into space. This mass loss will cause planetary orbits to expand rapidly, but it will also subject planets to bombardment by high-energy particles and dense streams of stellar material. For the outer planets and their moons, which might have been enjoying their brief period of habitability, these conditions will bring an abrupt end to any potential for life. The violent fluctuations in solar energy will alternately freeze and bake these worlds, while the intense stellar winds strip away any atmospheres that may have developed. The paradise phase of the outer solar system will end in a cosmic catastrophe. As the thermal pulses continue, they will dredge up material from deep within the sun's interior, bringing elements that have never before reached the surface. Carbon, oxygen, and even heavier elements created by neutron capture processes will appear in the sun's atmosphere for the first time. These elements will be carried away by the stellar winds, enriching the interstellar medium with the products of stellar nucleosynthesis. Eventually, the thermal pulses will begin to eject the sun's outer layers entirely. Each pulse will blow off more and more of the star's envelope, creating expanding shells of glowing gas around the central core. These shells will form what astronomers call a planetary nebula, one of the most beautiful phenomena in the universe. The creation of a planetary nebula is a gradual process that may take tens of thousands of years to complete. The ejected material will form concentric shells expanding at different velocities, creating complex structures illuminated by the intense ultraviolet radiation from the hot central core. The interplay between stellar winds of different epochs, magnetic fields, and the interaction with the interstellar medium will create intricate patterns of knots, jets, and spiral structures. From a distance, if any observers exist to witness it, the death of our sun will be a spectacular light show. The planetary nebula will glow in brilliant colors as different elements emit characteristic wavelengths of light when excited by the central star's radiation. Hydrogen will glow red, oxygen will contribute green and blue hues, and nitrogen will add deeper reds and purples. The nebula may be visible from thousands of light years away, a cosmic monument to the Sun's long life. At the center of this expanding nebula will be all that remains of our once mighty Sun, a white dwarf star about the size of Earth, but containing roughly 60% of the Sun's original mass. This incredibly dense object will have a surface temperature of perhaps 100,000 degrees Celsius, making it one of the hottest objects in the galaxy. However, it will have no internal energy source, so it will slowly cool over billions of years, eventually fading to a cold, dark remnant. The formation of the planetary nebula will mark the final destruction of any remaining solar system objects. The intense ultraviolet radiation from the central white dwarf will ionize and heat any remaining planetary atmospheres, causing them to escape rapidly into space. The powerful stellar winds will sweep away dust, small debris, and any remaining gaseous material. Large objects like planets and moons may survive as bare, rocky, or metallic cores, stripped of their atmospheres and any volatile materials. These remnants will orbit the white dwarf in darkness, receiving virtually no energy from their dying star. Any remaining atmosphere will freeze solid, creating worlds covered in oxygen and nitrogen snow under a black sky illuminated only by the faint glow of distant stars. The asteroid belt, which has remained relatively unchanged for billions of years, will be transformed into a different kind of debris disk. The thermal pulses and stellar winds will alter the orbits of asteroids, potentially causing collisions and creating new populations of dust and debris. Some asteroids may be completely vaporized by the intense radiation, while others may be pushed into highly elliptical orbits, or even ejected from the solar system entirely. Comets from the outer Kuiper belt and Oort cloud will experience their own transformation. The intense radiation and stellar winds will cause them to outgas violently, potentially stripping away most of their volatile materials. Those that survive may become dark, rocky objects, their icy compositions forever altered by their brief encounter with the dying sun. The duration of the planetary nebula phase will be relatively short, perhaps 10,000 to 50,000 years. During this time, the expanding shells of gas will gradually disperse into the interstellar medium, carrying with them the elements forged during the sun's lifetime: the carbon in our bodies, the oxygen we breathe, the calcium in our bones. All will be scattered across space, available to be incorporated into future generations of stars and planets. As the nebula fades and disperses, the white dwarf at its center will continue to cool slowly. Over the next several billion years, its surface temperature will drop from 100,000 degrees to perhaps 10,000 degrees, then 5,000 degrees, changing color from brilliant white to yellow to red. Eventually, after trillions of years, it will cool to the point where it no longer glows visibly, becoming a cold, dark object known as a black dwarf. During its slow cooling phase, the white dwarf will provide virtually no energy to any remaining objects in its vicinity. Planets that once basked in solar warmth will become frozen wastelands colder than the most distant objects in today's outer solar system. Their surfaces will be covered with frozen atmospheres, and their cores will slowly cool as well, eventually becoming solid throughout. The gravitational effects of the mass loss during the planetary nebula phase will cause the orbits of surviving objects to expand significantly. Planets that once orbited close to the Sun will find themselves in much more distant orbits around the white dwarf. The familiar architecture of the solar system, with its carefully spaced planets and predictable orbital periods, will be completely disrupted. Some objects may be ejected from the system entirely during the violent final phases of stellar evolution. These rogue planets and moons will wander through interstellar space, dark and cold, carrying with them the chemical signatures of their origin and our solar system. They may eventually be captured by other stars, becoming part of new planetary systems, or they may drift forever through the emptiness between stars. The end of our sun's life will not be unique in the galaxy. Similar scenes play out around countless other sun-like stars, each creating its own planetary nebula and leaving behind its own white dwarf remnant. The galaxy contains thousands of planetary nebulae, in various stages of evolution, each one marking the death of a star that once provided energy and stability to its own family of planets. In the longest view of cosmic time, even the white dwarf remnant of our Sun will not last forever. Over timescales so vast that they dwarf the current age of the universe, white dwarfs slowly crystallize as they cool, eventually becoming solid objects made of crystallized carbon and oxygen. Even these may eventually decay through quantum processes that operate over unimaginably long periods. But long before such ultimate fates play out, the expanding shells of our Sun's planetary nebula will have mixed with the interstellar medium, joining the complex ecology of gas and dust between the stars. This material will participate in the formation of new stars, new planets, and perhaps new forms life, continuing the cosmic cycle of death and rebirth that has been operating since the first stars formed billions of years ago. The story of our Sun's death is thus not really an ending, but a transformation. The elements that make up our world and ourselves will return to space, available to become part of future worlds and future life forms. In this sense, the death of the Sun represents not the end of our cosmic story, but its continuation in forms we cannot yet imagine, in places we will never see, under alien skies illuminated by stars that have not yet been born. In the final moments before Earth disappears forever into the expanding Sun, if consciousness still exists anywhere in our solar system, it would witness the culmination of one of the universe's most fundamental stories, the transformation of matter and energy across cosmic time. These last days would be simultaneously the most terrible and the most beautiful in the history of our world, as the forces that created our planet complete the cycle by reclaiming it. The approach to these ultimate moments would be marked by changes so profound that they would redefine the very concepts of day and night, earth and sky, matter and energy. As Earth spirals closer to the Sun's expanded surface, or finds itself already within the star's outer atmosphere, the familiar boundaries between planet and space would begin to dissolve. The horizon that has defined the human experience throughout our species' existence would transform into something alien and magnificent. Instead of the curved line where Earth meets sky, observers would see the roiling, turbulent surface of the Sun extending in all directions. The concept of up and down would become meaningless as gravitational forces from the Sun overwhelm Earth's own gravity field. The planet would begin to deform, stretched and compressed by tidal forces that dwarf anything experienced from the Moon. Temperature would rise beyond anything in Earth's previous experience. The rocks that have stood for billions of years would not just melt, but vaporize, their atoms dissociating into a plasma that glows with its own light. The very air, if any remained, would become luminous as its molecules are torn apart by the intense heat and radiation. Earth would transform from a solid planet into a glowing ball of plasma, its material beginning to stream away in comet-like tails. The magnetic field that has protected Earth throughout its history would become visible in these final moments, as the solar wind and Earth's own vaporizing material interact with the magnetic field lines. Brilliant auroras would dance, not just at the poles, but across the entire surface of the disintegrating planet, creating light shows of unimaginable beauty and violence. As Earth's material begins to merge with the Sun's outer atmosphere, the distinction between planet and star would fade entirely. The silicon and oxygen that once formed Earth's mountains, the iron that comprised its core, the carbon that was once part of living things, all would join the stellar material in the Sun's extended envelope. Earth would become part of the Sun, its atoms mixing with stellar material in a final, irreversible union. The process would not be instantaneous, but would unfold over thousands, or perhaps millions of years, depending on the specific conditions within the Sun's atmosphere. Different parts of Earth would vaporize at different rates, with lighter elements and compounds escaping first, followed gradually by heavier materials. The planet would essentially evaporate from the outside in, like a sugar cube dissolving in hot coffee. During this dissolution, Earth's material would undergo nuclear reactions that have never occurred naturally on our planet's surface. The intense heat and density within the Sun's atmosphere would cause fusion reactions among Earth's atoms, transmuting elements and creating isotopes that don't exist under normal planetary conditions. Carbon would fuse with helium to create oxygen. Oxygen would combine with hydrogen to form fluorine. The very atoms that once comprised Earth would be transformed into new elements, their identities changed by the nuclear furnace of the dying Sun. The gravitational effects during these final phases would be extraordinary. As Earth's mass spreads out within the Sun's atmosphere, it would create disturbances in the stellar material, potentially generating shock waves and turbulence that propagate throughout the Sun's envelope. These disturbances might affect the Sun's own evolution, possibly triggering additional thermal pulses or altering the timing of mass ejection events. From the perspective of the outer solar system, if any stable observational platform still existed, Earth's final moments would appear as a gradual brightening of the Sun. The additional material from Earth's dissolution would temporarily increase the Sun's energy output and might create visible changes in the star's color and spectrum. Spectroscopic analysis would reveal the signature of Earth's atoms as they burn in the stellar atmosphere, a final testament to the planet's existence. The duration of Earth's existence as a distinct object within the Sun would be remarkably brief compared to its 4.6 billion year history as an independent planet. The same world that survived asteroid impacts, ice ages, mass extinctions, and countless other catastrophes would be completely absorbed by its parent star in perhaps a few thousand years. This represents less than 1/millionth of 1% of Earth's total lifetime, a cosmic eye blink that ends a story spanning nearly a third of the universe's entire history. Yet, in that brief final phase, Earth would experience conditions more extreme than anywhere else in the solar system. The pressures, temperatures, and radiation levels would exceed anything that has ever existed on any planetary surface. In a strange sense, Earth would briefly become one of the most energetic and active places in the local universe, glowing with the combined energy of stellar fusion and gravitational collapse. The end would come not with darkness but with light. As Earth's material fully integrates with the Sun's atmosphere, the last traces of our planet would contribute to the star's luminosity. The energy that once drove Earth's weather, powered its ecosystems, and warmed its surface would be released in a final burst of radiation that spreads outward at the speed of light, carrying the news of Earth's transformation to distant stars. In the aftermath, no trace of Earth would remain as a distinct object. The careful spherical structure built up over billions of years through accretion and differentiation would be completely erased. The layered geology that tells the story of Earth's evolution, the fossil record of ancient life, the chemical signatures of past atmospheres and oceans, all would be thoroughly mixed and transformed within the stellar material. However, the atoms themselves would survive, enriched by their passage through the stellar furnace. When the Sun eventually sheds its outer layers to form a planetary nebula, Earth's material would be among the gas and dust expelled into space. The carbon that was once part of terrestrial life, the oxygen that filled our atmosphere, the silicon that formed our continents, would all become part of the interstellar medium, available to form new stars and planets. This dispersal would represent Earth's final gift to the universe. The elements that accumulated on our planet over its long history, concentrated and refined by billions of years of geological and biological processes, would be returned to space in forms that could seed the formation of new worlds. Future planetary systems might incorporate atoms that were once part of Earth's oceans or mountains or living creatures, creating a form of cosmic immortality even after the complete destruction of our world. The story of Earth's final moments thus becomes a story of transformation rather than simple destruction. Matter and energy cannot be created or destroyed, only converted from one form to another. Earth's final act would be to demonstrate this fundamental principle of physics on the grandest possible scale, converting planetary matter into stellar energy and eventually into the raw material for future cosmic evolution. In contemplating these ultimate events, we're confronted with questions about the nature of existence, meaning, and continuity that stretch far beyond astronomy or physics. What does it mean for a world to die if its constituent atoms live on? How do we understand endings when they're also beginnings? What is the relationship between the temporary structures we call planets and stars and the eternal principles that govern their behavior? These final days before the sun swallows Earth would represent the completion of a cycle that began with the formation of the solar system itself. The same gravitational forces that originally brought together the dust and gas to form our planet would finally reclaim it, returning its material to the star from which it ultimately came. In this sense, Earth's consumption by the sun would be less like destruction and more like a homecoming. The return of stellar material to its place of origin after a 4.6 billion year journey as a planet. The silence that follows would be profound, not the silence of death, but the silence of transformation complete, where once a blue marble spun in the darkness, carrying oceans and continents, and countless forms of life, there would be only the gentle expansion of stellar material, indistinguishable from the rest of the sun's atmosphere. The Earth that was would live on only in the light streaming outward from the sun, a final message written in electromagnetic radiation, traveling forever through the cosmos at the speed of light. As we reach the end of our long journey through deep time, from the present moment to the final days before the sun swallows the Earth, we find ourselves in a strange and contemplative place. We've traveled across billions of years, witnessed the slow brightening of our star, watched the death of Earth's biosphere, and finally seen our planet consumed by the very star that gave it life. It's a story that encompasses the longest possible perspective on existence, yet somehow brings us back to fundamental questions about meaning, continuity, and our place in the cosmic order. Throughout this journey, we've seen that endings and beginnings are intimately connected in the universe. The death of our sun will seed the birth of new stars. The destruction of Earth will provide raw materials for new planets. The elements forged in our star's core and distributed by its stellar winds will someday become part of other worlds, other atmospheres, perhaps other forms of life entirely different from anything we can imagine. This perspective offers a unique form of comfort in the face of ultimate endings. While the Earth we know, the life we cherish, and even our sun itself will not last forever, they are part of something much larger and longer lasting. The atoms in our bodies have already lived through countless such cycles, having been forged in the hearts of ancient stars that died long before our solar system was born. We are made of recycled starlight, temporarily organized into the patterns we call matter, life, and consciousness. The vast timescales we've contemplated serve to put our daily concerns in perspective, while simultaneously highlighting the preciousness of our current moment. We live during a brief golden age when Earth is perfectly positioned in the habitable zone, when the sun is stable and benevolent, when the conditions for complex life are as favorable as they will ever be. Every sunrise we witness, every season that passes, every generation that lives and loves and passes on its knowledge, occurs during this cosmic sweet spot that will not last forever. But perhaps the most profound insight from our journey into deep time is the recognition that even the most seemingly permanent things are temporary. While the deepest patterns and principles persist across unimaginable spans of time, stars are born, live, and die, but the physical laws that govern stellar evolution remain constant. Planets form and are destroyed, but the elements they're made of continue their cosmic journey indefinitely. Life emerges, evolves, and faces extinction, but the potential for complexity and consciousness appears to be written into the fundamental structure of the universe. In contemplating the final days before the sun swallows the Earth, we're not just thinking about endings, but about the nature of time itself. The universe operates on scales that dwarf human experience, yet it produces structures and phenomena that we can understand and appreciate. Our brief existence as conscious beings allows us to witness and comprehend cosmic processes that span billions of years. In a sense, the universe has evolved the capacity to understand itself through beings like us, making consciousness a cosmic phenomenon rather than merely a terrestrial accident. The story we've explored is not science fiction, but science fact, based on our best understanding of stellar physics, planetary science, and cosmic evolution. While the specific details may change as our knowledge improves, the broad outline is as certain as any prediction can be across such vast timescales. The sun will brighten, enter its red giant phase, and eventually consume the inner planets. This is not a possibility, but a certainty, written in the fundamental physics that governs how stars evolve. Yet, knowing this future doesn't diminish the meaning of the present. Instead, it amplifies it. We are privileged to live during the sun's most stable and benevolent phase, when Earth provides a perfect platform for the development of life, intelligence, and culture. Every moment of existence is borrowed time, made possible by the delicate balance of cosmic forces that creates temporary islands of complexity in a universe trending toward entropy. The beings who might witness Earth's final days, if they exist at all, would be products of evolutionary processes so extended that they might be as different from us as we are from the earliest microbes. They might have spread throughout the solar system, adapted to survive in conditions we can barely imagine, or transcended physical existence entirely in ways that are currently beyond our comprehension. Or they might be visitors from other star systems, witnesses to a cosmic drama that plays out around every sun-like star in the galaxy. Regardless of who or what might observe these ultimate events, the story itself would be magnificent. The transformation of a planetary system, the death and rebirth of stellar material, the endless cycling of matter and energy through ever-changing forms, represents the universe engaged in its most fundamental activity, the organization and reorganization of complexity across space and time. In our current moment, we are part of this grand story. Every breath we take, every thought we think, every act of love or creation or discovery we make occurs within this vast context of cosmic evolution. We are not separate from the universe, but expressions of it, temporary patterns in the flow of matter and energy that briefly achieve self-awareness before returning to the cosmic stream. The sun that warmed your face today is the same sun that will someday expand beyond Earth's orbit. The atoms in your body are the same atoms that will someday be scattered by stellar winds to seed new worlds. The consciousness that contemplates these vast timescales is made possible by the same physical processes that govern the birth and death of stars. We are intimately connected to the deepest processes of cosmic evolution, not as observers but as participants. As our imaginary journey comes to an end, we return to the present moment with perhaps a different perspective on time, existence, and meaning. The daily dramas that occupy our attention are no less important for being brief, but they exist within a context of such grandeur and scope that they partake of cosmic significance. Every human life, every act of creativity, every moment of understanding contributes to the universe's exploration of its own possibilities. The final days before the sun swallows the earth are still billions of years in the future, but they connect directly to this moment through the unbroken chain of physical processes that link past, present, and future. The light from the sun that illuminates these words was created by the same nuclear fusion that will someday drive the star's expansion. The gravity that holds you to Earth's surface is the same force that will eventually cause our planet's destruction. The elements in your body were forged in ancient stellar cores and will someday be recycled through similar processes. In the end, the story of Earth's final days is also the story of its birth, its evolution, and its participation in the larger cosmic drama. It's a story without true beginnings or endings, only transformations, cycles, and the eternal dance of matter and energy through space and time. We are privileged to be conscious participants in this dance, able to perceive its patterns and appreciate its beauty, even as we acknowledge our own temporary place within its grand choreography. So as you close your eyes tonight, perhaps you can rest in the knowledge that you are part of something immeasurably vast and ancient and ongoing. The atoms in your body carry the history of the cosmos. The energy that powers your thoughts was generated in the heart of our sun, the very capacity for consciousness that allows you to contemplate these ideas may be one of the universe's greatest achievements, a way for the cosmos to know and appreciate itself through beings like you. The sun will continue to shine for billions more years, steadily warming our world and providing the energy that makes all Earth stories possible. In that gentle light, life will continue to evolve, love will continue to flourish, and consciousness will continue to reach toward understanding. These are the gifts of our cosmic moment, the temporary but profound possibilities that emerge when matter and energy organize themselves into the patterns we call planets, life, and mind. Sleep well, knowing that you are part of the longest story ever told, a story that connects the formation of the first atoms to the final fate of stars. A story in which every moment matters because it contributes to the universe's ongoing exploration of what it means to exist. The final days before the sun swallows the earth are also, in the deepest sense, the first days of whatever comes next. The continuation of the cosmic story in forms we cannot yet imagine, but of which we are forever a part. Sweet dreams, fellow travelers in time and space. The universe continues its ancient dance, and you dance with it, brief and bright and beautiful, a momentary flowering of consciousness in the vast garden of cosmic time. Rest now, and let the great story carry you forward into tomorrow and all the tomorrows to come, each one a gift from the stars that made us and to which we will someday return.